Welcome, everyone. My name is Jonna Vuoskoski, and I'll be chairing the proceedings today. Master of Science Connor Spiech will later today defend his dissertation publicly for the PhD degree. The title of the dissertation is Predictive and Dynamic Mechanisms of Rhythm and Groove. Connor Spiech will now give his trial lecture. The topic for the lecture was set by the committee. He will lecture on the neural basis of beat perception in relation to predictive coding theory. Connor Spiech, the floor is yours.
Yeah, so like Jonna said, the trial lecture topic that I've been assigned is the neural basis of beat perception in relation to predictive coding theory. So that's a lot of jargon, so we're going to start by giving you some definitions here. What I mean by beat is just this sense of regular, steady pulse underlying a rhythm, and beat perception is merely your ability to extract this information out of the rhythms that you're listening to. So to make that a little bit more explicitly clear, I've got a few different examples here. We're going to start with this Ein, zwei, Polizei by Modo. It's a great example of a rhythm where the beat is strongly, strongly emphasized. That wasn't supposed to happen. Off to a great start today.
Gute Nacht, Ein, zwei, Polizei, 3, 4, Grenadier, 5, 6, alte Keks, 7, 8, gute Nacht.
So as you can hear there, the beats are highly stressed with these very powerful bassy kicks. But in the second example, every beat isn't necessarily stressed, but you still get a very strong sense of underlying pulse. And so this is Get It Right by Aretha Franklin. And in this final example, the beat might be a little bit strange to you if you're a Western listener, but let's give it a listen. So even though it might be a little bit more complicated and less predictable, I think everybody still kind of gets that sense of underlying pulse. And I realize we're not in full screen anymore over here, so I can change that. Yeah, so how do we measure this beat perception ability using people's behavior? So the first class of tests that you can use are called psychoacoustic tests. So these are things like the beat alignment test, parts of the Harvard beat assessment test, and the rhythm component of the Swedish music discrimination test. But there are plenty of others. And just to give you an idea of what that's like, I've actually got one of these loaded up on my computer here. This is one that I've used in my experiments. It's the computerized adaptive beat alignment test. So you're going to hear a couple of clips of music. It's the same clip presented twice, but with two different beat tracks. One of them is going to have the beat track aligned to the beat, and one of them will be misaligned. And your job in the audience is to tell me whether the first or the second track was more aligned. All right, so show of hands who thought the first was more aligned. Okay, what about the second? Okay, we're just going to say second, and again, I didn't program this, so this is actually very annoying. But in the bottom right corner, it's going to show whether this was correct or not, and it's immediately going to start playing the next musical clip, which is jarring, but we need to complain to the Goldsmiths people about this. All right, so once again, first or second? We got a lot of hands for first. What about second, just for the hell of it? We're gonna go with first. All right, what are we thinking on this one? First? Looks like we got one. Two. And what about the second? All right, let's see how we did then. All right, well, 2 out of 3 ain't bad. It could be worse. So these are psychoacoustic tests. These are measuring pure listening abilities at finding the beat. And then the other class of tests that you can use are called production or synchronization tests. So a beat production test asks subjects to tap the beat themselves without music. And then synchronization tests ask the subjects to tap along to the beat of the music while they're listening to it. So it's synchronizing their movements to the beat. And both of these classes of tests assume that people need to be able to perceive the beat in order to move to it. But some interesting research coming out now might show that that's not necessarily the case. So a friend of mine, Valentine Bagel, he found a few beat-deaf individuals who couldn't perceive the beat, but could still miraculously produce a beat just fine. And then also some work coming out of Frankfurt right now with children shows that beat production abilities might mature faster than beat perception abilities. So maybe just something to keep in mind here. So now that we know what beat perception is, how do we perceive the beat? What's it like? So some beats sound stronger or louder than others, like you hear stresses that aren't necessarily in the sound. Whereas others might sound a little bit softer or weaker. And so this hierarchical grouping of strong and weak beats is known as meter. And I'm going to illustrate that here. So for those of you not familiar with musical notation, this just says bop, 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 bop. Simple enough. But in your head, especially if you're a musician, you might count this as 1, 2, 3, 4. 1, 2, 3, 4. It's not supposed to slow down, but we're lagging a little bit. So we tend to hear these kinds of so-called subjective accents, even if they're not physically present in the sound. So I've got another little test for you guys. This talk is very test-heavy in the beginning. And you're going to tell me whether all the notes in the sequence were the same loudness or if some were louder than others. Same loudness or different? Let's see hands for same. All right, hands for different. Okay, we'll try another one. All right, same loudness. Well, that's disheartening. Different. Thanks, Jamie. We'll try another one. Same and different. Okay, last one. All right, same or different? Same? No same, okay. Good, it was different. So, yeah, this one physically created the stresses on the ones by just manipulating the volume. This one is supposed to induce, at least in about half of you, it did induce like illusory loudness differences because of the timbre. So they changed the sound, basically, of the one. This one, in the lab anyway, it induces illusory loudness differences using microtiming, so it slightly jitters the timing, so it wasn't 100% isochronous, evenly spaced in time, that is. And this actually was just an isochronous metronome, so like everybody spotted that one. That's good. So this implies a sort of internal clock that predicts the timing and the nature of future sounds in a sequence and how they're going to sound to you. So because some sounds are more expected than others, we can do some studies on this. So an early EEG study looked at the neural effective meter, and this was Burchard and colleagues in 2003. So they used something called an auditory oddball task, which I'm going to break down in a minute. And they looked at whether these unexpected, surprising tones would differ if they were presented on the strong beats or on the weak beats. And so yes, I know auditory oddball task is maybe strange to some of you, so we're going to do one real quick. Just like real music. So in this oddball task, the oddballs are the boops. Those very low tones. And so these elicit a very strong surprise response in the brain. In this case, we're talking about the P3 component, which I'll break down in just a second. And yeah, this surprise response, theoretically, should be stronger when it's presented on the strong beats compared to the weak beats, because the strong beats are more expected than the weak beats. And so you see the P3 here. So P3 is referring to the third positive going wave. I'm not going to explain to you why the scale is upside down. It's some stupid things from the EEG people. But basically, you see the first, second, and then the third positive peak. Maybe you can't see it so well up here, but this is the surprise response to the weak beat deviant tone, and this is the surprise response when the boop was presented on the strong beat. So you see a stronger surprise response on the strong beats. So this is meant to illustrate that metric expectations literally shape our perception of sounds and how they are experienced. And so to hammer this point home a little bit further, I'm going to talk about this study done by Sylvie Nozarodna and colleagues in 2011. So they looked at these steady state evoked potentials, which again, this is EEG jargon for the brain's responses to repeated stimuli. And they found that these change depending on what meter you're imagining. So they presented another stream of like beeps. So this is just isochronous beeps, beep, 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 beep. No boops in this one. And they asked subjects to either sit there and just passively listen to it, or they asked them to count them. So 1, 2, 1, 2, 1, 2, or they counted them 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And so what they found is that when they looked at these steady state responses in the brain, the frequency that people were counting, so the rate that people were counting, in the brain, these frequencies were enhanced. So here you see in the so-called binary condition, when people are counting 1, 2, you see enhanced brain responses corresponding to the rate of the 1, 2 counting. Similarly, when people counted to 3, you see responses in the brain that are elevated for the frequency of this 1, 2, 3 counting. So this is really, really neat, and there's a large-scale replication study of this going on, multi-center, all around the world, so stay tuned. And that's that. So why am I telling you all of this? What's going on in the brain? How can we explain this? Well, this wouldn't be a very interesting trial lecture if I didn't have some kind of answer to that. So I'm going to introduce you to the grand unifying theory of the mind, as Andy Clark puts it. This is probably its biggest proponent, Carl Friston here. And he describes it succinctly as, in the 20th century, we thought the brain extracted knowledge from sensations. But in the 21st century, we witnessed a strange inversion in which the brain became an organ of inference, actively constructing explanations for what's going on out there, beyond its sensory epithelia. Old Carl always has a way with words. So what does all that mean? What are the key points? What do you need to remember? Well, first, predictive coding posits a hierarchical organization of the nervous system where you have bottom-up sensory information, so like sounds coming into your ears, and this is being compared to top-down expectations about what kind of sensory information you're going to experience next. So when this comparison happens, the difference between what you're expecting to experience and what you're actually experiencing is called prediction error. And under predictive coding, the goal of the brain is to reduce this prediction error. So I'm going to try to sell you on this using a really fancy illusion. You're going to hear 4 sets of noise sounds. And first, you're going to hear a patch of noise. You're probably not going to understand anything unless you've heard this presentation before. And then the second time, some speech will be said. And then the third time you're going to hear the noise, something miraculous is going to happen. And there are 4 examples of this.
Bagpipes and bongos are musical instruments.
Bagpipes and bongos are musical instruments. The high-security prison was surrounded by barbed wire.
The high-security prison was surrounded by barbed wire.
The high-security prison was surrounded by barbed wire.
The full moon shone brightly that night. Move the garbage nearer to the large window.
Yeah, so I kind of like the black metal kind of vibes they're giving off in those last couple examples. Very fitting for Norway. But yeah, I hope that everybody was able to understand the speech hidden in the noise on the third presentation, right? Yeah, it's pretty crazy. I've heard this so many times that I hear it on the first presentation, so it's ruined for me, but hopefully the magic will live on in you. So how do we explain this? Well, as predictive coding kind of says, you've got this bottom-up sensory information, in this case, the noisy sounds coming into your auditory cortex over there. It's called the temporal lobe. And then this feeds information up to higher cortical areas where you have expectations about the sounds. But the first time you listen to the sound, you don't have any expectations, you just hear noise. So, your brain is kind of like, whatever, it's just noise, I don't know what's going on. However, the third time you hear the noise, now you know what to listen for. And so you have these top-down expectations in place, saying, it's the full moon shone brightly that night, right? And so now when you hear the noise, you can pick it out, and you sharpen and enhance the precision of your prior expectations so that you can hear this speech hidden away in the noise. And so what is precision? And prediction error correction. So before I go on, I need to explain that there's a bunch of different ways that this has been posited to happen in the brain. Predictive coding is a big framework, lots of different rules, and I'm just going to explain one of them today. This is one of the more popular ones. It's called Bayesian inference, or Bayesian updating. So, a lot of words, but I'm going to explain using this fancy little graphic here on the right. So, basically, you've got 3 different distributions here. You've got one representing incoming sensory evidence, one representing your prior beliefs, and then you multiply them together, and essentially you get a new updated belief. So to explain this a little bit further, the shape of this distribution is reflecting it's how trustworthy it is, or how reliable or how precise it is. So if the distribution is really, really sharp, this is something that you trust a lot. It's very precise. If your distribution is kind of wide, well, it's something that you don't put a whole lot of stock into. So, I can explain that here with this example over here. So, say you're looking out into a sandstorm, and all of your precision is weighted towards this new sensory information that's coming in. So, the sandstorm. You really just trust your eyes here. You don't have any strong beliefs. This distribution is very flat. You don't have any strong beliefs about what you're expecting to see in the sandstorm. And so when you multiply these together, your new updated belief about the world that you're looking at, still a blurry mess, right? Still just the sandstorm. However, on the opposite end, you could theoretically have a very strong belief that, for whatever reason, there might just be a camel wandering out in this desert, and you really, really, really believe that it's out there. And you don't really trust what you're seeing so much. And so in this case, when you multiply these distributions together, you see you don't trust your sensory evidence, and you really, really trust your prior beliefs. You might hallucinate and see a camel that's not actually even there. So to kind of put this in context with the last example, You can think about B representing the first time that you heard the noise, where you didn't have any strong prior beliefs, and so you just hear noise. And C is probably something closer to the third time that you heard the noise, where now you have very strong beliefs about what's in the noise, because you trust me as a scientist for whatever reason, and so then you hear the speech. So, how can this explain beat perception? Well, under predictive coding, beat perception is an active process of inferring the steady pulse from these rhythms that vary in terms of how regular and steady they actually are. So, under this view, meter is one type of prior that you can use to predict the beat of rhythms. So this is one type of prior belief. You know, you're listening to some kind of music, you expect, you know, the 1, 2, 3, 4 if you're a typical Western listener, for example. And so those subjective accents that we were hearing earlier are just a consequence then of these top-down predictions about the beat, enhancing the precision of the actual sounds that you're hearing. But now the question arises of, like, well, do we actually have any evidence of this? And we're going to start by talking about where in the brain this might be happening. So, long story short, it probably happens in, at least for beat perception, in auditory and motor areas. And by motor, I mean the parts of your brain relevant for moving your body around, moving your meat sack. So, this is mostly based on this study from Chen, Penhuen, and Zatori that's been replicated a bunch of times now, where they had people lay down in an MRI scanner and tap their fingers along to some music, and then they also had them lay in the scanner and just imagine tapping along to the music, and then critically, they had them just lay in the scanner and listen to the music, and what you see is that the same brain areas that are active when you're tapping along to the music, albeit much weaker, are also active when you're passively just laying there and listening to it. So a couple of different theories have kind of emerged about this. One is that, well, you know, we're just simply imagining moving our bodies. It's just an involuntary thing that we just imagine that we're moving along. And this is the so-called shadowing or mirroring account. But then some predictive coding people take a little bit more of a radical stance on this. And they would say that the motor cortex is causally involved in perceiving the beat. So you need your motor cortex to actually perceive the beat. And so this is called the action simulation for auditory prediction hypothesis. And you can kind of think about, like, when you're actually moving along to music, your motor cortex, the activity is just so great, it's breaking out of the simulation, so to speak. So, let's talk about the ASAP hypothesis then. So you got your brain here, you've got your incoming auditory information coming into auditory cortex over here, and it feeds up into motor areas in the brain, which then feed back information about the beat and predicting where the beat's going to occur, and this comes down and it shapes your new perception of the sound. So when you hear the next sounds coming in, your motor cortex is saying, okay, is this occurring where and when I thought it was or not? And so this has some pretty interesting implications here. So again, the motor system under this theory plays a causal role in beat perception, therefore it's necessary. And so were you to say disrupt the motor system somehow, this should mess up your beat perception ability. So for example, you can imagine maybe having a stroke that affects your motor areas, and theoretically these populations should be worse at beat perception. But we also have a more fun and safe way to test this as well, using a technology called transcranial magnetic stimulation, where you can kind of artificially, temporarily turn off different parts of the brain. And so Ross and colleagues here, they did just that, and they disrupted this part of the brain over here called the parietal lobe, where these predictions are coming back and they're starting to be integrated into the auditory system. And yeah, so when they knocked it out, they found that people performed much worse on that beat alignment test that we all did earlier. So that was the one with the musical clips and the beep tracks. So people performed worse on this after this kind of stimulation. So this does kind of support the idea that the motor system is causally involved with beat perception. So now we know where this might be happening. Now the question becomes how. How is this implemented? And so some predictive coding people think that bottom-up auditory information maybe encoding the prediction error signals, are encoded in this really, really fast brain activity called gamma. Whether it's a real oscillation or not is another question for another day. But this gamma activity encodes bottom-up sensory information, and your motor predictions are encoded in this slower brain activity called beta. And so Fujioka and colleagues did a few studies, if these plots will load, where they found that when people were presented with some tones, so that's what these little black boxes represent, they hear the tone, and you see this big spike in gamma activity right after the tone is presented. But interestingly, even when you omit a tone, you still see a big spike in gamma activity as if the brain is expecting that tone to be there, even though it wasn't. In the beta band, however, you see something a little bit different. So after the tone is presented, around 200 milliseconds later, you see a decrease in beta activity that then ramps right up to the next tone. So it's as if it's predicting the presence of the next tone. But when the tone is omitted, you don't see this big decrease, but you still see this ramping up in anticipation of the next tone that actually is there. And then in a 2015 study, they replicated this beta result, and they also showed that this is sensitive to meter and metric expectations, which is really, really cool. But yeah, so there might be some problems with the gamma stuff. People in the field are kind of skeptical about this result. It's not been super widely replicated, not yet anyway. But the beta results are pretty trustworthy, I would say. So now that we know about these predictions, how they might happen, how they might be implemented, we can ask, how did we get them? Where did they come from? So we've got a few different ways to acquire these beat-based expectations, and one is through enculturation. So just growing up someplace. You know, you're exposed to a lot of different kinds of music, a lot of different kinds of beats, and yeah, in this sense, you just kind of acquire these beat-based expectations through passive absorption. So some people here, Rainer Polak, for example, along with Nori Jacobi, they did this really, really ambitious study where they tested people all around the world, really. You can see here on the map where they all went, of varying levels of ability. So they had non-musicians and musicians and professional dancers and all of these different people, and they asked them to play a sort of rhythmic telephone where they were played a random sequence of tones, and then they had to tap what they just heard. And then their taps would be recorded, and an algorithm would then adjust. It would adjust the next sequence of tones based on what they tapped back into it. And so in a way, this would kind of go on for a while until it sort of levels out and stabilizes. And the idea here is that when it stabilizes, this is reflecting the closest thing that people can relate to in their culture, the closest ratio of rhythms. And so when they did this, they found some things were universal. So there seems to be this preference all around the world for just isochrony. So just bop, 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 bop. That's the 1-1-1 there. But then there were also some culturally specific sorts of rhythmic priors or beat-based expectations. So, for example, in West Africa, but another way that you can acquire these beat-based expectations is through formal training. So if you just practice playing music for a while. And so this is supported by studies that show that musicians tap more accurately and more stably than non-musicians. And they're also better at that beat alignment test that we did earlier. Another way that you can acquire these things is just through pure rote memorization and you know, familiarizing yourself with the music itself or the beats in a specific piece of music. So in this study, people were walking more in sync with music that they had already heard before compared to music that they had never heard before. So now that we know all about where these sorts of things come from, I'm going to focus on the consequences of the predictive coding account and the sorts of things that it might predict. Namely, how it relates to groove, because this is what I work on. It's what I'm most familiar with. And so they've got this. This is the hypothesized explanation for groove. And it's quite dense, I guess, but you've got rhythmic complexity here on the x-axis. And then you can think about syncopation as the degree to which the stimulus gets more complex. Precision is the opposite of that. So as it gets more complex, it's supposed, your precision and how much you trust that sound is supposed to decrease. And we're going to start with that. So, I don't know why it's presenting two at once, but as a rhythm becomes more complex, the sensory precision about the rhythm's auditory inputs should decrease. So, put more simply, as a rhythm gets more complex, the more it starts to sound like noise to you, the less you trust it, the less you focus on it. So, what are the hypotheses that we can develop based off of this? Well, we should see better neural encoding for simpler rhythms compared to complex rhythms. And prediction errors for simple rhythms should be more salient. They should stick out more than they would for more complex rhythms. And this would be consistent with Brochard and colleagues' earlier results that I presented at the start of the talk with the increased P3, the increased surprise response for strong beats compared to weak beats. But it's been a while since I played you any music. I've done a lot of talking at you. So I'm going to play a couple of musical clips here to illustrate what I mean by rhythmically simple, very precise kind of music, and then more rhythmically complex and less precise music. Yeah, I'll let you guys take a guess as to which one that was. Yeah, so the best part about giving these talks is that I can just impose my really terrible music taste on everybody else. But basically, the point here is that in this track here, it's very, very simple. If someone in the band were to make a mistake and something were to occur at an unexpected location, this would really, really stick out to you. You would notice immediately. However, I'd wager that for most of you in this room, if somebody played something a little bit off in this musical clip, the second one, you might not even notice. You might think it was intentional. So, some researchers did not using real music, but they used beeps again. And they looked for this kind of surprise response in simple rhythms versus in very complex rhythms. So again, they were using this auditory oddball experiment, except this time instead of beeps and boops, the boops, the unexpected deviant tones, were things that were shifted a little bit earlier in time. So they had small and large deviants, but here I'm just going to talk about the small deviants. So in this first low complexity stimulus, everything was isochronous, so just beep, 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 beep. And then sometimes one of those beeps would come a little bit earlier, so beep, 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 maybe something like that. And the unexpected faster one, you would see a big surprise response, hypothetically. So with the medium complexity condition, they used two different tone intervals. So this might be something like beep, 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 something like that. And then again, they would shift one of these in time so that it would be a little bit unexpected. And then finally, they had a very complex condition where there were 4 different intervals. I'm not even going to bother trying to explain this. It sounded kind of noisy and very unexpected and random, okay? And so what they saw in the brain using a different surprise signal in the brain called the mismatch negativity, they saw that in the low complexity condition, when this unexpected note was played, you see a very big surprise response, but then as it gets more complex, this surprise response kind of diminishes until it doesn't really exist much at all anymore in the high complexity condition. So when you're exposed to really complex sounds and everything, you don't have any predictions left, you don't assign much precision to what you're hearing, and so you don't get this big surprise response. So we've got even more evidence of decreasing sensory precision here. So I'm going to harken back to Sylvie Nozarodin and friends again, and in 2016 they did another study using these steady state evoked potentials. So the brain responses to these repeated notes in a sequence, and they used 2 different rhythms, a simpler one here called unsyncopated, and then a more complex one called syncopated. So you can just think about this as being simple, and then this one as being complex. And the reason why this is more simple is because at the beat locations, you actually have events. So the beat is being physically stressed by the sound more. Whereas in the complex one, sometimes the beat is missing. And so you have to infer it. You have to imagine it there, okay? So that's what makes it more complex. And what they found is that the brain's response to the rate that the beat was going was greater for the simple rhythm compared to the more complex rhythm. They played this at different speeds as well. That's maybe not so important here. So, do we have any evidence for the precision-weighted prediction error part, though? So, if you remember, that was this inverted U-shaped part. So as the stimulus gets more complex, as the rhythm gets more complex, you start to trust it less, and out of this, you're supposed to get like a nice inverted U-shape where you have prediction errors that are very, very predictable, only at moderate levels of complexity. So I can try and break this down a little bit more. I know that this is kind of dense and jargony. But put simply, while you're listening to these moderately complex rhythms, we basically know when the beat is going to be skipped, kind of, by the stimulus. So if I go bop, ba bop, ba bop, ba bop, you know that where you might tap your foot in the gaps that I've left there in the sound. And so the idea here is that we move to music, you know, this pleasurable urge to move our head or tap our foot to the beat. We do this because we're explicitly trying to correct these prediction errors that we know are going to occur in the rhythm. And so in this way, our own movements direct our attention away from the distracting, more surprising elements, I guess, in the music. And so they reinforce our perception of the beat, our best guess as to where the beat is. And so at low levels of complexity, we don't have any urge to move because there's no surprise. We know exactly when things are going to happen. We don't need to move. Whereas at really high levels of rhythmic complexity, it just starts to sound like noise. We don't have any predictions. We don't know when errors are going to occur. We wouldn't even know what an error would be in this context. So we don't want to move to it because we can't. But in the middle, we've got this groovy sweet spot where we know when the errors are going to occur, and we know how to correct them with our own movement. We have a good idea of where the beat is, and so we stress the beat by moving our bodies. So, now I'm going to talk about this method that I've been using for a while now. It's called pupillometry. I'm allowed to use these images without citing them because that's my eye actually up there. Thanks to Bruno for recording this. So you can see that my eye is actually changing when the light gets flashed into it. So this is called the pupillary light reflex. But when you flash a big light in your pupil, it constricts really rapidly. So this is also used as a diagnostic tool to see if you have neurological damage. Think I'm healthy. And down here, I've got a trace of what this looks like when I do my experiments. So I've got the pupil size being plotted over time. And so people are listening to different kinds of music here. And in one condition, they're just sitting there and listening, and so that's this condition. And so you see a big dilation, and then it kind of starts to taper off. But then when people are actually moving their bodies to the music, you see a giant peak. So what's going on here? Well, our pupils dilate when we're paying more attention to something. So you can think about if you're effortfully trying to solve a difficult math problem in your head, your pupils are going to be dilating a lot. And so this has been linked to a chemical called noradrenaline. You might recognize it more as like the fight or flight instinct. So this is known as like arousal. And under predictive coding, these highly precise prediction errors are really deemed important. And so they should demand more attention. So theoretically, your pupil should dilate more in the middle of this inverted U shape, so at moderately complex rhythms. And so, this could reflect the prediction error signal itself. So these really precise prediction errors might be, really jolting and they make your pupil dilate. Or, the pupil response could reflect the mental effort and the attentional resources needed to correct those very precise errors. It's not a perfect measure, but it gets us in the ballpark. And so what kind of academic would I be if I didn't plug my own work a little bit? So I did a couple of studies, which hopefully will be published later this year, where I found just that. At moderate levels of rhythmic complexity, these drum beats that people were listening to evoked the moderately complex drum beats anyway, evoked the biggest dilations of the pupil. So yeah, we had various kinds of drum beats in this study here. I reanalyzed some data that I published in Scientific Reports in 2021, and then this is from an EEG study that'll be coming out hopefully soon. I hope to submit that soon. So, almost done. Just want to check in and ask if I've sold you on predictive coding's explanation for beat perception. You know, it's not everybody believes in this. So I'm going to give you some of the pros and cons here. In my opinion, the greatest advantage of this predictive coding framework for beat perception is that it really neatly explains the flexibility of our top-down predictions and on how we hear the beat. So, you know, that Sylvie Knows a Rodden study where it was just a bunch of beeps and people imagined counting it in 1, 2 or 1, 2, 3. Predictive coding is really, really convenient and elegant at explaining something like that, where despite hearing the same exact sound, you can consciously choose to hear it differently. And this has measurable effects. However, some people would say that, you know, this elegance is maybe not such a good thing because it, you know, it explains maybe too much. It seems to some people that, you know, maybe it's a little bit incredulous that, you know, the whole goal of the brain is just reducing prediction error. You know, one critic of the big theory is that, well, if the goal was to reduce prediction error, why aren't we hanging out in a dark room all the time? But, you know, there's some responses to that. But I'm not going to get into that. However, you know, some of the other challenges, I think, with predictive coding is, and this is one that I tried to hint at earlier, is that it's a lot of the neural evidence is still correlative, and some of it, like the gamma results, haven't really been replicated so much or so consistently. So a lot of the neural evidence is mixed. And besides the TMS study, a lot of it is kind of indirect. So we're still looking for that prediction error signal in the brain, and we're looking for how these predictions actually correct that prediction error. And our own Alejandro Blankman here has just got like $1 billion or something from the Norwegian Research Council to look for this in the brain. So he's going to be using local field potentials and single unit recordings, I think, in epilepsy patients. So stay tuned. Maybe we will find evidence of this. But then there's another class of criticisms, I think, of predictive coding. So opponents will argue that, you know, it feels a little bit like this, where, you know, you've got like this little man in the head pulling levers and predicting everything, and, you know, it doesn't seem very parsimonious, is the criticism. So especially the people from the dynamic attending theory camp, so this is people like Ed Large, Carolyn Palmer, Mari Rees-Jones, they don't think that we really need these top-down predictions at all. You can actually explain a lot of this stuff, they say, using bottom-up entrained oscillators. So, you know, music is rhythm, it occurs at a rate, and then they say that our brains kind of have different sampling rates. You know, so your brain has waves that go up and down over time. And when you listen to music, for example, your brain waves kind of sync up with this music that's going on out there in the world. And that actually this synchronization, this coupling between your brain waves and the musical waves, this kind of explains all of this stuff. This is how you perceive a beat in the dynamic attending theory. I mean, that could be its own lecture. But that's the gist of it. So, with that, I'm going to leave you with a big, intimidating wall of text here, talking about what I hope that I've conveyed to you today. So, one is that humans can perceive a steady underlying beat in music across a range of rhythmic complexity. Beat perception seems to be hierarchical, you know, when you group things into strong and weak beats, and predictive. So some strong beats are more expected than others, the weak beats. And then these metric expectations shape when and how we experience future beats and future sounds. This might be going on in motor and parietal cortices, where the predictions are coming down from your movement areas, and they shape your auditory perception. These top-down sensory motor predictions might be encoded in the beta band in the EEG. Bottom-up auditory prediction errors may, and I'm going to stress may, be encoded in the gamma band, or the gamma activity. might not be a band. And then beat-based expectations are acquired through enculturation, formal musical training, for example, and just simple rote memorization. And then neurophysiological encoding of the beat, so your brain's response to the beat worsens as it becomes more difficult to extract that beat, for example, when the music becomes more complex. And the pleasurable urge to move our bodies to music might be a result of this prediction error correction. But it's all still just a theory, so we've got to keep on testing, right? And so with that, I'd like to thank you all for your attention.
I would like to thank Connor Spiech for his lecture. I would also remind the audience of the public defense of his doctoral dissertation today at 12:15 in the same place.
Please rise for the procession.
Please be seated. Welcome, everyone. My name is Jonna Voskoski, and I will be the chair of this defense today. Master of Science Connor Spiech is about to defend his doctoral thesis entitled Predictive and Dynamic Mechanisms of Rhythm and Groove. On the 2nd of September 2022, Connor Spiech submitted his thesis to the University of Oslo and requested the opportunity to defend it for a doctoral degree. Professor Bruno Lang from the Department of Psychology at the University of Oslo has been the main supervisor for the dissertation, and Associate Professor Tor Endestad from the Department of Psychology at the University of Oslo has been the co-supervisor. Following the proposal by the Department of Psychology, the Faculty of Social Sciences appointed the following people to serve on the evaluatory committee. Professor Elvira Brattico from the Center for Music in the Brain from the Department of Clinical Medicine at the University of Aarhus. Professor Jamie Riley from the Department of Communication Sciences and Disorders at Temple University. Professor Rolf Reber from the Department of Psychology of the University of Oslo. The committee has come to the unanimous conclusion that the thesis is worthy of defense. The Faculty of Social Sciences has agreed to this. The candidate held his trial lecture earlier today, 17th of February 2023. The topic for this lecture was set by the committee: the neural basis of beat perception in relation to predictive coding theory. The committee found that the trial lecture had been held to their satisfaction. What now will follow is the viva, or the public defense of the thesis. The following two people have been appointed to serve as official opponents: Professor Elvira Brattico as first opponent, Professor Jamie Riley as second opponent. Everyone in this room is entitled to serve as an ex auditorio opponent. If anyone present wishes to do so, he or she will be given the chance to speak after the two opponents have finished and are asked to report their request to me before I invite the second opponent to begin. Today's schedule will be as follows. The first opponent will give an account of the thesis, followed by her contribution and the discussion between her and the candidate. This will last for approximately 1 hour and 15 minutes. That is until 1:30. We will then take a break until 1:45. Please remember that the schedule is tentative and subject to the dynamics of the discussion. After the break, we will hear from the second opponent. Finally, any ex auditorio opponents will be yielded the floor. I hereby call upon the first opponent.
Okay, good afternoon, and thanks to the faculty for appointing me as first opponent of this dissertation. So, as anticipated, I will provide like summarized account of the dissertation first, and next I will start discussion with the candidate. And I will have questions listed in the slides for facilitating the discussion. So the dissertation title is Predictive and Dynamic Mechanism of Rhythm and Groove. And it contains 3 studies which are reported in 3 separate papers, of which one is already published and the other ones have been submitted or archived in public repositories. And so I will present the results and the main points of the studies one by one. And first I will give just a brief introduction to the topic. And the topic is groove. And nicely in the thesis, Connor Spiech provides a summary of the 3 conceptualizations existing in the literature of groove, which have been put forward by Kamara and Danielsen in 2018. The first one is the conceptualization which has mainly or is most popular among musicians and musicologists, so that groove is a type of rhythmic pattern and performance style of music. The second conceptualization is what psychologists and neuroscientists actually favor, and groove is intended as the pleasurable urge to move. So this drive to follow the beat and do something with the beat, either tapping or even dance. And the third conceptualization is the pleasing, effortless, and timeless state of playing music, which is a concept that is most popular and favored by phenomenologists or philosophers as well. And here the thesis focuses on the second idea of what is groove. So, and indeed, it operationalizes groove by ratings of urge to move and enjoyment. So combining these 2 affective and motoric aspects of subjective perception of groove. But how can we manipulate sounds to become groovy, more or less groovy? And one way to do it is to manipulate the rhythm and its complexity. And complexity here is conceptualized as a cognitive cost. So the cost that we have psychologically in maintaining the metrics, so in keeping the beat. So either in terms of perception or production. So either in terms of understanding the beat in the music, how clear it is or not, or how well can we tap to a beat. So the more complex the music is rhythmically, the more difficult it is to track the beat. And one way to quantify complexity and manipulate it is to actually insert syncopation. So syncopation occurs with onsets on metrically weak accents, so as opposed to when they should come, so on the strong accents, or rests or time notes on metrically strong accents. So you put rest in the strong accent when you are expecting the accent, or you move you move the accent to the weak beat. So another way to manipulate complexity is pickups that also occur at metrically weak accents, but the sequence some beat is present rather than omitted. And another feature that can be manipulated is microtiming deviation. So you can shift the beat by up to 10 milliseconds, and you introduce complexity via this variability in the metric, in the meter. And finally, you could make the pulse more or less clear. So you could manipulate complexity also by increasing or decreasing actually the pulse clarity, which can be quantified computationally, for example, as an autocorrelation of the curve of the sound event onsets. And to explain groove theory, which is a predominant theory nowadays of a brain function, has been put forward, and namely the predictive coding theory, originally by Carl Friston and applied to explain groove by, for example, Peter Wust at first. And the predictive coding theory proposes that, and now I take the words, I borrow the words of Connor, that groove-induced movements help to resolve sensory ambiguity regarding musical pulse and meter, thus minimizing prediction errors stemming from structural deviations like syncopation. So this kind of theory has been first applied to groove by Maria Witek and colleagues in 2014 in a survey study with 50 funk drum breaks, showing an inverted U-shaped relationship between syncopation and desire to move. So what does it mean? It means that actually there is a sweet spot in how much we are urged to move to a rhythm. And it depends on the moderate metric complexity. So the sweet spot is when the complexity is moderate as opposed to low complexity or high complexity. And this is because with low level complexity, there is a little prediction error to resolve. So we know very well when the beat is coming. So there is no need for moving to find, the beat or to reinforce the beat model that we have in our mind. And with high complexity, we are lost. So we have little precision. So the middle, the moderate complexity is what actually makes us move the most. And as I mentioned, this was demonstrated in the first in this study, and then replicated many other times, also with neuroimaging evidence. But now in the thesis, Connor introduces a new way to, or a more novel way to measure groove, and it's recordings of pupil size with pupillometry. And why this is relevant for groove literature is because pupil dilates when we attend to something in the environment, and it's related to the fight or flight reflex. And this is governed by the locus coeruleus via the norepinephrine transmission. So we know that norepinephrine encodes reliability of sensory precision. So it is a very good way to understand more about groove. And for measuring cognitive error necessary for prediction error minimization in groove, we can then use pupillometry. And there are some initial findings, which are also mentioned in the thesis by Bowling and others, and Skansar and others in 2019. But the thesis provides additional progress in this field of applications of pupillometry for understanding groove perception. So the first study is exactly about this. So how we can use pupillometry to obtain physiological correlates of beat predictions and rhythm perception. And how it was done by using an eye tracker, infrared eye tracker for continuous monitoring of the pupillary surface area. in 30 participants while they listened to music clips varying in rhythm complexity. And participants also rated the clips for enjoyment, urge to move, and arousal. So the dependent variable was the pupil drift, so which is basically the rate of returning to baseline between the first beat until the last beat of the clips. And so, and this was intended as a measure of attentional disengagement. And additionally, participants were also assessed for their beat perception abilities with a computerized adaptive beat alignment test, the CA-BAT test. So these are examples of, or these are actually the stimuli used, which varied according to complexity levels. So there was a low complexity stimulus. Okay, you understand how it sounds. And so this is an example with the pickups. So now another drum beat with the syncopation. And then this is actually the sweet spot here, the pickups and syncopation. I anticipate the results here. So, and then there are two other stimuli which are with high complexity. So this one is completely random, so it's even more complex. So in the last ones, the metric model is very hard to follow. So the results then actually replicate the inverted U-shape relationship between rhythm complexity and behavior or urge to move and also enjoyment. So the two subjective correlates of groove. So indeed, adding slopes for rhythm complexity improved the model fit for all ratings, but the quadratic model was the one that fitted the data more than the linear model for urge to move and enjoyment. So this is basically the U-shape, inverted U-shape relationship, the quadratic model. Moreover, when Connor split the sample into high versus low beat perception performance groups and having 15 participants in each group, then there were differences, so that the participants with low performance in a beat perception ability had more like a linear trend for enjoyment. So you can see here that it's less quadratic, the relationship for the low performance group. Moreover, the presence of syncopations resulted in greater ratings of urge to move enjoyment and also perceived arousal, regardless of pickups presence. So what about pupillometry results? So here, there was a significant effect of repetition of these drum beats, but also repetition by rhythm interaction. And this is why the analysis focused on the second repetition to remove some of the noise or unwanted effects. And here, again, the quadratic model was the one that fitted the pupil drift rate data better than the linear model. So again, this showed a relationship which is shaped as an inverted U curve. And when splitting again the participants into high versus low beat perception abilities, the significant quadratic trend was present only in the high ability group. So there was the inverted U shape, particularly in those who are actually good with detecting the beats. And a bit less, it was flat, linear relationship with the low bit perception people. And there was also a main effect of pickups, but not of syncopation. So the summary of the results for the study 1 is that moderately complex rhythms, so the syncopation plus pickups, evoke the highest ratings of urge to move and enjoyment, depending on the individual beat perception ability. Also, rhythms rated groovier were associated with more sustained attention as measured by the pupil size drift rate, depending on beat perception ability. Moreover, interesting findings were obtained with the features pickups versus syncopation on groove. So the pickups elicited greater pupil dilation, while syncopations did not. Moreover, syncopations resulted in higher groove ratings, while pickups exerted no effect on ratings. So the interpretation by Connor was that while syncopations generated metrical uncertainty that may demand resolution through movement, pickups strengthened the internal model that could be used instead to guide movements. These movements are then used to reinforce the metric model itself in a feedback loop. So moving to study 2, according to the predictive coding theory, the groove consists of active inference to minimize rhythmic error. So they tap into the beat. So this sensory motor feedback helps resolving these errors, and it would actually increase the pleasure and the groove as compared to passive listening. And this is the main hypothesis that needs to be tested, because surprisingly, there is no, or there was no evidence in the literature about this. And so how this was tested? So the subjects were instructed to either synchronously tap their foot to the beat or passively listen to musical clips that varied in rhythmic complexity. Also, subjects rated again the clips for urge to move and pleasure, and also perceived energy, song familiarity, and style preferences. And the latter ones were used to control for these other confounding variables. And the dependent variables were groove ratings, pupil size, tapping intensity, which was measured with a contact microphone put close to the foot, which recorded an audio signal. So again, the participants were assessed for their beat perception abilities with the CIA BAT test. And there were 49 participants, and there were actually plenty of musicians here. So 34 of them played one instrument and 20 actively. And here, as compared to the previous study where the clips were a bit more artificial, the clips were actually from commercially recorded music, and from different kinds of musical styles, ranging from rock to jazz or EDM. And they were varied in rhythmic complexity, as actually measured with the MIR2 box, and particularly the function MIR pulse clarity, and using the entropy autocorrelation algorithms. They were about 8 seconds long here. I just show you a couple of examples of these 16 clips. Another example. So the second one is clearly a bit more complex than the first one. And there are quantitative values of complexity here measured with MIR2 box. And let's see the results. So behaviorally, again, the quadratic slopes were replicated with rhythm complexity in relation to urge to move and pleasure. And when the years of playing were included in the model, there was even a slight improving of the model fit. And another improvement was given by including foot tapping condition here. So the foot tapping condition was really winning in terms of quadratic model as compared to the listening condition. And in contrast, a linear slope was the winning model for rhythm complexity when using perceived energy ratings as dependent variables. And there was, for the perceived energy ratings, there was no effect of foot tapping. So this extremely nicely proves the hypothesis, and even in comparison with the control condition of perceived energy ratings. And the pupillometer results are a bit more complex here. So the two-way ANOVA for pupil dilation showed the main effect of condition, so that the tapping actually dilated more the pupils as compared to the passive listening, probably related to attention engagement here. But with the mixed ANOVA for tapping variability, it was shown that the tap variability increased with the rhythm complexity and decreased with a higher bit perception ability. But there was no interaction. So this means that here there was no sort of U-shaped curve relationship for the pupil dilation dependent variable. And the tapping intensity measure was also related to rhythm complexity, so that the more certain the participants were when tapping, or the more the intensity was reflecting the certainty into tapping, so that they were tapping stronger where they were sure about the beat in the music. So let's move to study 3. So the study 3, the aim was to understand how expertise affects music abilities, and specifically whether active music training is necessary for influencing musical abilities, and specifically beat perception, or whether once perfected, these abilities remain even without active practicing. So the scope was to understand if the use it or lose it principle of brain plasticity is valid, actually, in relation to beat perception. And here the CA-BAT scores from the three datasets are combined. Two of these datasets are the ones coming from the previous studies I just presented briefly. So there were 97 participants classified into active musicians, inactive musicians, and non-musicians. And this beat perception ability test was lasting about 10 minutes. It was an adaptive test with pairs of short musical clips with overlaid beat tracks, and one of which was on beat and another one was aligned. So the participant had to choose the beep track aligned to the beat. So the results here showed that there was a main effect of musicianship, with active musicians better than inactive musicians or non-musicians. And with the regression analysis with machine learning algorithm, only years of music training was a significant predictor for beat perception ability, and no other music-related or demographic variables had any effect. So what does it mean? It means that when there was adequate music training, then the beat perception got better, and it also remained good for a while, for years, even without active practicing in these people. So overall, the thesis shows many interesting findings, and there is a summary that I actually mutated from the thesis itself with some of my edits. And the edits are actually that I put in bold characters the ones that I find the most innovative original findings. So the first one is more, it is actually quite original, but it is also replication of the previous literature, namely that syncopations are important for eliciting groove ratings. And what is very novel is that the finding that the pupil drift rate indexes groove ratings in drum beats. And also pickups elicit greater pupil dilations. It's a novel finding. And another novel finding is that actively synchronizing to the beat by tapping increases groove ratings and also pupil dilations. And the tapping becomes softer and less precise with increasing complexity. And the inverted U-shaped curve between rhythmic complexity and groove is stronger for real music than synthetic drum beats. And this is also pretty novel finding here of the thesis. And finally, greater beat perception is associated with more musical training, more precise tapping, and more prominent inverted U-shaped curves. And this finding is a replication of existing literature. So now we come to the questions. So I have a few questions that I grouped them by topics, so to speak. And I think I have, or we have about half an hour. Yes, no, a bit more, 45 minutes for discussion. So I can see Connor is ready. So the first question. So the first one is a curiosity about tap intensity, because it was interesting and I think quite original measure which was chosen, thanks also to the clever idea to use contact microphone for the study, the second study. So why the listener would tap stronger instead of just only more precisely when certain? What are they aiming to when they tap stronger? Yeah.
Yeah, so my thought with the tap intensity finding was just that people tend to tap softer when they're less sure of where the beat is. And my thinking there was like they just don't want to introduce even more noise. Like, their variability got higher, so they were tapping less precisely. And so I think they're aware of that. And so they don't want to make the rhythm even more complicated to themselves by adding their own noisy taps into the mix.
So yeah, so it is more like a negative sort of explanation. So that it's not that they tap louder, but they don't tap softer when they are certain. So they are sort of inhibited to tap when they are uncertain, but they just tap normally when they are certain of the beat.
Yeah, that's the way that I saw it.
Yeah.
But I think we need more work on it.
Yeah, thank you. Oops. Let's see. So another question is about again the tapping intensity. So, and about how all these findings would relate to the brain, to neuroimaging. So, what are the main findings on the topic? I mean, you already covered in the trial lecture, but how would you relate these findings of study 2 to brain research? Or would you imagine a study to look into this?
Yeah, I mean,
of course, there are technical issues here because, of course, the tapping creates some noise there. But how would you relate this? Yeah, to the brain findings.
Yeah. So I guess the issue of like tap intensity is that it's often not even measured, mostly just because of the technology, right? So we put people in front of a computer. We give them a button box and they press it on the keyboard, and a lot of the times that doesn't register tap intensity. So I actually struggled to find any kind of like citations in the literature at all on the tap intensity kind of result. But I don't know. I mean, I would assume that when people are tapping more intensely, maybe these beat perception networks would be more activated, but I guess somebody has to do that study.
Mm-hmm. Yeah, I mean, I think that it's really, I find this study or this finding and the methodology applied really fascinating for for this predictive coding research field, because in previous studies we asked participants to evaluate how certain they are, so how confident they are about their answers. And it's again self-rating. And of course, you can measure also the brain responses and correlate them with the ratings. But here you have actually motoric measure that you can quantify, and that you might be much more reliable than self-ratings of how confident you are about something that you have to think over. So which might fluctuate depending on your metacognition skills. So, but when you tap, it's really quite immediate.
Yeah, I would, maybe somebody's already done it, but it would be really, really cool to see like the lateralized readiness potential with this kind of intensity, to see if that also scales kind of with the intensity of the taps, maybe in the latency or in the amplitude of this lateralized readiness potential. And the other great thing about that is that we know how to measure that from the foot. So you could do an exact same kind of recording with the contact mic on the side of the shoe, and then just strap them up with the EEG and see what happens.
Actually, there is Maria Erohio Ruiz from Goldsmith in London, who has been working with this error-related negative potentials when playing notes on a keyboard. So anticipating the mistake and relating these findings with the predictive coding theory and active inference, assumption or predictions. But but I don't think anybody has done anything much more simple, like just checking the tapping and also error negative potentials before. Yeah, that would be actually a cool study. Okay, so next. Another question about pulse clarity as one of the features, again, in study 2 that you use for measuring rhythm complexity in relation to groove. There is another interesting concept in the literature, namely pulse salience. And I think that you implicitly use that concept because you restricted the choice of the beat per minute around 100 because it was what is most natural. I think you argued something like that. But was it done based on musicology literature, or was it done thinking about this other psychology literature on pulse salience?
Yeah, so Justin London has some work showing, and I think it's been replicated by other people too, but generally I think a lot of natural body movement rhythms and stuff coincide around 120 beats per minute. And I think a lot of at least Western recorded music is around 120 beats per minute. Ideally everything would have been matched to 120 directly, but it was really, really difficult to find controlled enough clips that varied, so we extended it to 10 beats per minute in either direction, so 110 to 130. But yeah, with beat salience and everything, it's almost kind of paradoxical because at very, very simple rhythms you have high beat salience, but even at moderately complex rhythms you also have a pretty salient beat. You're moving your body to it, so clearly it's got to be salient to you. And then it's really only at high complexity that the notion of the beat itself kind of breaks down. So in a way, it's almost kind of paradoxical, or maybe it's just nonlinear,
Yeah. But is it so that the groove phenomenon is restricted to where the pulse is most salient, or is it something that it varies depending on the complexity itself?
Well, I think groove is highest at moderate levels of complexity. I mean, for some people, for very simple stuff too. But the beat would be very, very salient in the very simple rhythms as well, and theoretically, it could be as salient, or it could be even maybe a little bit less salient, depending on how you're quantifying that or defining it. So I think at moderate levels of rhythmic complexity, the beat salience from the rhythm itself is maybe less salient, but I think your subjective notion of its salience is probably on par with really simple rhythms. But yeah, I mean it's a matter of how you define and quantify these things, I think.
So so you are saying that the tempo itself is not really
Well, just like the
a
structures,
feature.
the structures with the syncopations. Like, so sometimes you're gonna have, like in the trial lecture, with the Eurobeat stuff, like all of the beats are emphasized by the bass drum, whereas like in the Aretha Franklin example, like some of the beats are kind of omitted, so you don't get the salience from the sound itself. It's some kind of like mental salience that you kind of impose on it, I guess, because of musical expectations and stuff that we have.
Yeah, I'm just going around the question. So basically, my question, I mean, to put it more straightforwardly, is that could there be any groove in a very slow tempo?
I think it's not so common. I think people have a hard time synchronizing their beats. I don't know the cutoff off the top of my head, but I think it's around 60 beats per minute or so is when people start to have trouble kind of like tapping that kind of consistently. So I would imagine, yeah, I mean, I mean, subjectively, when I was going through with all these clips, like all of the grooviest stuff was like faster than 130 beats per minute, and often more syncopated. So, but yeah.
Yeah. So maybe the tempo could be also one of the features. At least for it could be listed.
It for sure plays a role. I just just to keep this simple and everything, we just kind of treated it as like a controlled thing, you know.
Yeah. Okay, so next set of questions about styles. So well, actually, I pick up here one sentence that popped up from the thesis. So you wrote, "Not all music fills us with this irresistible urge to move our bodies to, for example, the Gregorian chant," which begs the question of why. So why? My question is actually your question. So why is there music that does not make us move? What could be the function of such music? It's a very, very broad question, but
well, I mean,
you kind of put it yourself.
Well, I think that there's like a lot of different ways of listening and ways to appreciate music. And so like, you know, kind of hearkening to like the two main motivations for listening to music. You either listen to music that you kind of already matches your emotions at the time, or you listen to it kind of prescriptively to kind of put you into the mindset that you want to be in. So for music that doesn't make you want to move, you know, maybe, you know, you're just feeling kind of chill or glum or something. You're not really trying to get off the couch, you know, you just want to relax, you know, and so you just listen to music, like ambient music. I mean, maybe Gregorian chant. I don't know if we have any Gregorian chant fans in the audience, but, you know, that kind of stuff to either put you in the mindset of being more relaxed or to stay kind of relaxed. I mean, the first thing that comes to my mind.
Yeah. I mean, of course, I mean, one could go back to all the evolutionary theories about origins of music, but maybe we don't need to do that now. Okay, so I move to the next question. So, so this is actually something that interests me a lot when reading the thesis, because in study 2 you found that tapping did not interact with the rhythm complexity for the pupil dilation. So the pupil responded to increasingly, complex rhythm in the real music. But then there was, in the study 1, there was the U-shaped curve, or another, actually, for the pupil drift rate. So, so you mentioned an explanation in the thesis, but I wanted to hear more about this discrepancy in the results between the two studies.
How much time do we have? Because I've got a lot of... yeah, I mean, so like the cheapest explanation is just like, well, you know, you're listening to very long clips of drum beats, so 20-second long drum beats versus 8-second musical clips. So, you know, I did look at the drift rate and I calculated it a half a dozen different ways. But, you know, it was never as principled as in the first study, because the first study we had discrete repetitions, like loops of each drum beat. So you could calculate the drift from the start to the end of a single repetition. Whereas with the real musical clips, you know, they all had varying tempos and stuff, and they were a little less controlled in this sense. So there wasn't really one principled point to, like, you know, select for to calculate the start of the drift rate. And the other thing is that, like, you know, the pupil is sensitive to just pure attention, right? And so people could be attending to a dozen different things in the musical clips. Whereas in the drum beats, there's really nothing else going on except for the rhythm. So I think it's kind of SNR stuff a little bit, but yeah.
Yeah, but actually this leads me to another question, related question. So what would you do to find this U-shaped curve with real music? Because that's where we want to go, actually, I think, at the end. I mean, to study the groove phenomenon with realistic sounds.
No, I'm working on this right now. I mean, I dread having to ask people how they feel about anything, you know. So I would much rather just have like a nice physiological measure, just like, oh, you know, the pupil's dilating. I know for sure 1-to-1 that this metric actually tracks groove. But you know, things like longer trials and everything, because I think what happens with the pupil, I've got this other metric that I'm working out, trying to write it up as a methods paper later this year, but you know, I need to test it on other data sets. But the thing is you need like kind of long trials, so longer than 10 seconds, because that's about how long it takes for people to like fully hit floor.
Exactly.
Once the pupil dilation response kind of is at floor and is like kind of returned to baseline after that big orienting response, which is that first dilation you see in the series.
Yeah.
Once you're back to baseline, then you can just correct the signal and z-score the dilations from there, and then you can measure the amount of evoked dilation from this baseline. And so far, on a couple of different drum beat stimuli sets, data sets, and everything, it works. But I'm working on ideally applying this to real musical clips too. So,
actually, this again leads me to another question. Which is why you actually chose so short clips in the first place. I mean, in my research, when I have applied naturalistic paradigms, I actually tend to use the real. I mean, when I use real music, I use all of it. So why to restrict to just 8 seconds? Was there? I mean, what was the original rationale for that?
Well, I mean, we were hoping that the pupil dilation response would be, we could just average the entire window, and that we would see the effect with rhythmic complexity like that. So that was the initial thinking, is that like any longer than 8 seconds, and we are going to have to contend with this drift and the baseline corrections and all this more complicated analyses. And we were just trying to keep it simple. You know, we could cram more stimuli into the set if we kept it short. But yeah, I mean, it's just a series of trade-offs, I guess.
Yes.
And the other thing is that a lot of those clips actually had vocals in there, and vocals would screw
yeah.
You know, so we had to kind of like do a little bit of surgery, excising around the vocal points and that kind of thing.
Yeah, and I think which leads actually to the next question, if I remember right, what I put in there. Yes, which means that, I mean, clearly there has been some sort of personal musical taste there, a little bit like your trial lecture. And if I think about my personal musical taste, I love Latin American music, and there is no such a single example of salsa, samba, merengue, bachata, you know, whatnot, dance kind of music, so which are actually really driving to move. And so why not? And would you expect some different results or the same results or better results with this kind of Latin stuff?
I mean, the simple answer is just like, you know, I'm a pretty square white guy. You know, I don't listen to salsa. So,
yeah, I'm not much into salsa. I can see that.
I wouldn't know where to look. And the other thing is, like, I couldn't tell you like what simple salsa versus complex salsa sounds like. I will say that in the online study that I've done now with a couple people here, we do have a little bit of samba and stuff in there. So it works generally, but like, yeah, I guess. Well, you could kind of have two hypotheses here. Like, you know, these genres that strongly correlate with like dancing and stuff. You could imagine that you might get like some kind of association effect where you just get higher groove based on like, well, you know, in my culture, this music is only for dancing. So you might actually, it might kind of act as a confound even, unless you have the full range of complexity across those genres, you know?
I don't know, I wouldn't agree with that, but I would rather say that, I mean, when I think about some of the excerpts or type of songs that could be used, and I'm actually building right now a study where we are picking up on those songs. I mean, the difficulty is not to start dancing. I mean, that's more a complicated confound. So, like, really keep the participant like still.
Yeah.
especially those who love this kind of music. I don't know if you had the same kind of issue with yours. Because of course they were like instructed very clearly to just stop, but did they actually move other parts of the body along with foot?
Not that I could visibly see. I mean, they were in a separate room, so you couldn't spy on them. But I didn't hear them tapping on the desk. In the first study, actually, with the pupil drift rate, there were a couple of subjects who were like drumming on the desk with it. And then even more strangely, like one of the subjects was drumming along to the random drum beat. So,
Okay, yeah, you always have this kind of weird participants in all the studies.
Very, very highly trained musician though. So like, 100 beats per minute, 4/4, even a random drum beat is like pretty simple to someone like that. So I guess they were just trying to spice it up.
Yeah. Okay. Yeah, but maybe it will be interesting to control for the other kinds of body movements as well.
Yeah, somebody should do a mocap study on it.
Yeah, it will be interesting too. Okay, so in the final set of questions, if I remember right, and we are going to the expertise then. It's the final aspect here. So, so again, about some design choices especially in study 2, but not only. So that because you were actually targeting experts as well, but somehow you decided to use this perception test, and you proposed in the discussion of the final part of the paper that you would perhaps in the future screen beforehand participants with this test. And so my question in relation to this choice of design and maybe future choice of design. So by not actually targeting percussionists or people with higher, familiarity with dancing kind of music, like the Latin Americans or African participants and so on. Yeah. So is there a specific reason for it, or just because you prefer this objective ways of testing?
Well, I mean, we definitely should test like expert percussionists and like people from different cultures. Absolutely, that needs to be done. I think for me, it's like the Kabat is 10 minutes, so it's like it's really, really quick. It's pretty easy, and the other thing is like it's kind of hard, I think, to find these experts sometimes, and also, I do kind of like the quote unquote objective nature of the Kabat. It's got its problems maybe, but like, the nice thing is that I have like a number which is easier to feed into the regression, and these categorical distinctions, unless you make them really, really large, it's given me problems before. So when I was using some of for example, it's like I could have used musical training as a covariate in the first study. It works just as well, but like the Kabat just fit a little nicer, when I was using the psychoacoustic test. So, I mean, just for pragmatic reasons, I kind of favor the Kabat, but like people definitely should look at real experts, and especially from different cultures.
Yeah, I mean, I guess that the expertise itself brings up additional kind of issues like the ones that you mentioned just earlier, that even the random rhythms might sound easy, and then you want to actually, they might become too actively inferring rhythms. So there might be other issues there.
And so like, for example, they weren't the winning models when we plugged hours a week that people play music. They were like a little bit less parsimonious than the model without that covariate. But when we did plug it in, what we saw is like, we didn't see a nice symmetrical inverted U shape anymore, except for the people who don't play music. So the people who don't play music weekly have the nice symmetrical inverted U. But the people who play music every week, they see something much closer to like just a positive linear trend, which makes sense. These are people who are actively playing music every week. They can tolerate and groove to and move to and enjoy more complicated music, I guess.
So. This is also the results obtained by Thomas Matthews in our lab. Yes. Well, that would be actually interesting. But I think that studying more, even like specifically rhythm experts would be really nice in this kind of research.
I'm sure it would be cleaner for sure.
Yeah, yeah.
Because the other thing is like, yeah, okay, you recruit expert musicians and everything, but you know, you don't know what kind of music they play.
Yeah, exactly.
You know, like it could be some real, you know, arrhythmic kind of music, like ambient soundscapes and stuff. They could be an expert at that, but you know, I don't know if they'd have better timing or something because of it. You know.
Yeah, yeah. Of course, there is an issue about you know, recruitment. So yeah, in Aarhus we have tried in the study. Initial studies by Ole Högli, we actually aimed only at percussionists, but it was extremely hard to find them and convince them to come to the lab. So of course there are also sort of pragmatic, you know, decisions that one has to make, which are not only, it's always a trade-off about what you want to study and how you can do it.
Yeah, especially when you're bringing people into the lab, you know, it's it can be tough.
Yes, exactly. Okay, let's see what I have next. Yeah, yes. The other one, again, about the Kabat test, or CABAT, how I call it. So you seem to favor that a lot. It's very short and it's nice and quite sort of ecological type of test, because it uses nice clips and so on, but it didn't. Sorry, study 3 didn't discriminate between active and inactive musicians, but could there be also because there was a sort of plateau, so that basically it's not difficult enough test, because I'm aware of tests that might be more complicated.
Yeah.
So have you tried other kinds of musicality tests that could be better at, you know, reaching up the high level skills of musicians, active musicians?
So I personally haven't tried any other tests, but I mean, obviously, like the musical ear test, I think gets it more of these metrical expectations. But the reason I didn't use that is because it's still pen and paper. So Peter needs to make a digital version of this and put it on the internet. Once he does that,
I can give you an update. It is actually in the internet. It was not done by Peter, but by a Canadian group. I think led by Glenn Schellenberg, if I remember right. Yeah, so it does exist in the internet. Yeah.
Yeah, then we should test differences then.
Yeah, and that is actually pretty hard. So even if you are a musician, you could actually miss some of the items.
Yeah, I participated in it a few times. It's not super easy towards the back half of that one.
Yeah, so I think we are reaching the end of my questions at least. Let's see. Yeah, I think we are doing fine with the time. So, okay, now about dance. So I'm just thinking again about the rest of the body, but you sort of answered to it already. So you already mentioned that it would be interesting to have a mock-up type of setting. But would you actually expect the same kind of findings as obtained with the tapping, so that there would be actually a better quadratic fit in when you add the dance or some sort of body movements?
I mean, I think it might depend on the kind of body movement, but I'm not really sure, because I know Dan Cameron is doing like a lot of this like dancer kind of research with this inverted U shape. And he's having kind of a tough time of it sometimes. Like, sometimes it might depend on the kind of dance that people are doing. So I don't know. I think it might just be messier. I think, tapping your foot is something so easy that pretty much everybody can do it rather effortlessly. Whereas dance, it involves so much more, and I think people are using different parts of the body for different kinds of rhythmic features. And it would just, somebody should do this, but not me. Too complicated.
There is actually a Karageorgis study, I think just came out or last year, with Peter Woos's last author, where they tried to look into this issue as well. So it might be worth checking also where the literature is going with respect to dance and U-shaped curve for groove. And again, about expertise. I think that we have talked about percussionists so far, or musicians and percussionists, but there are also dancers, like, the salsa, salsa dancer, or these Latin American dancers who are very much into this kind of music. And I don't know if there would be any effect of even dancing expertise, or would you expect?
Yeah, I mean, I think it's going to depend on how expert they are, for one, and then also I think the kind of expert that they are. So like I think certain kinds of dancing styles that's more integrated with the music, and like dancing that is kind of part of the music making, I would expect the effect to be stronger, but this is just kind of hand wavy armchair kind of thinking right now.
Yeah. Yes. Okay, let's see next. Okay, and then finally, again, I am borrowing a sentence from the thesis. At the end of the thesis, you write that longitudinal and intervention-based studies manipulating and controlling for these various factors should thus be carried out to conclusively rule out the influence of these variables. So there are, of course, some longitudinal studies, but looking into how you can learn to become better at beat perception, or I don't know if there is much about specifically targeting groove perception, but would you be interested in this kind of design, or are you considering doing this kind of studies?
Personally, no.
No.
maybe after I get tenure, and then I have time to think more than 2 years at a time. Yeah.
Yeah, that's really wise.
The ideal situation, though, you would have like this, 20-year stretch or something.
Yeah.
Genetics information from everybody. They're twins, and some of them are learning music, some of them aren't.
Yeah.
Some of them start learning and then they stop, and you got several 100,000 people like this. This would be tight, and somebody should do that. But
so when you direct your own center of excellence, then you can.
Yeah, I'll hire a small army of PhD students to carry out this study on my behalf.
That's a good plan. Okay, so I think that I'm actually finished with my questions, which were quite plenty, and I'm very satisfied with the answers and with the future plans that you have. And so I think that's all for me. No, actually, sorry, there is the last one. Sorry. Surprise. Prediction error here. So the very last question, which is actually the broader one, or even broader, because it's about theoretical implications of your research, and that's something that you already started thinking about in the thesis, but I wanted to hear your words about it, because you of course mentioned critiques to using only predictive coding to explain this wonderful phenomenon of groove, and also for explaining pleasure in music. And so, and you also mentioned the dynamic attending theory also in your trial lecture. So what are your thoughts about which theory is winning over which, or can they be integrated to explain groove, and in which way you could actually use both of them, if you want to use both of them to explain groove?
Yeah, so you saved the hornet's nest question for last, I see.
Yes.
Yeah, I think people get really tied into these things, like emotionally. But I don't know, I see them as kind of compatible. The way that these predictions could be corrected and signaled and stuff could very well be due to entrained oscillators in the brain. We've got good evidence for both theories. I mean, dynamic attending, I will say, is easier to falsify, because it's if you don't observe the entrainment, it's not dynamic attending. So it's easier to falsify. I think predictive coding has a lot of strengths, namely that the effect of the top-down influence on low-level perception. So I think that, especially the fact that you can hear the same rhythm in different kinds of meters. I think that's pretty compelling evidence for some kind of top-down predictive process. Whether you call it predictive coding or you call it a higher order entrained oscillator, to me, I don't care. But like, maybe I'll have to care soon.
Yeah, but I think that you said very important very important thought about the fact that predictive coding theory is harder to falsify than the dynamic attended theory. I think if I follow what you said. Because in a way, it's hard to imagine when we are not predicting. It's
So the issue with predictive coding right now is like we don't have a surefire direct measure of the error, of the prediction error itself. And so until we have that, I don't think it's going to be super easy to falsify it, because in the meantime, it's easy to say, well, we just weren't looking for that just wasn't prediction error. We've been looking in the wrong place, So once we have if we ever get surefire evidence of this is a prediction error signal in the brain, if we get that, then predictive coding is right on the table as just as falsifiable, I think, as dynamic attending.
Yes.
But there's lots of
I agree with that, and I think that the work you are doing at Rhythm about intracranial recordings is really extremely valuable for answering this important point. Yes, so I think this is the real end of my questions. No more surprises, and I wish to thank you for a very nice discussion, and yes, and then I would like to finish with one sentence from Jean-Paul Sartre. I'm going to smile, and my smile will sink down into your pupils, and heaven knows what it will become. I found it a very nice poetic close for this discussion. So thanks again.
Yeah, thank you.
Thank you.
I would like to thank our first opponent and the candidate for their efforts. There will now be a break until 1:45. Please be seated. We will now continue the public defense of the candidate's doctoral thesis. I hereby yield the floor to the second opponent.
Thanks.
And defense. One of the things that we noted in reading your document, a couple things. The rigor and the control of the experiments, the stimuli was outstanding. Your best practices in open science, disseminating your code, and promoting reproducibility were also outstanding. Your innovative applications of drift and pupillometry that we're going to ask you a little bit about methods, and there are very well-grounded connections between data and theory. One of the comments that we noted in the report to Connor was that the complexity, density, and technical rigor of the writing sometimes made the interpretation somewhat challenging at times. So you're a great writer. It's also very dense, and it's dense material. So the first challenge I have for you is if you ran into a friend from high school in the elevator and you did the 2-minute elevator speech of what is your research and why is it important, what would you say?
Well, I actually get this a lot, so I have a lot of practice with this one.
Good.
So off to a good start, yeah. Now what I tell people is I research why we move to music, and I think that I'm testing a theory that says that it has to do somewhat with maybe this is too close. It has something to do with predictability, the predictability of the rhythms that we're listening to, and so far, at moderate levels of rhythmic complexity, we seem to have this uncontrollable urge to move our bodies to the beat, presumably to make it more understandable to us. So to make the rhythm sound simpler, I guess. Is that satisfactory?
Yeah, that's satisfactory. Good, thanks. Second was getting into more of the technical aspects of what you were doing with pupillometry.
Yeah.
So people who aren't necessarily super familiar with pupillometry, the pupil is nice as a biophysical signal in that it's just one channel that's continuously changing over time. So you have surface area that's changing over time, which is nice compared to multi-channel stimuli. It's nice, but it's also deceptively complex. So most pupillometry studies in the past, it assumes there's some discrete event, which they call a delta function, just like in functional imaging where there's like a target detection on, off, infinitesimally short, and you model some response to that. So most, probably 95% of pupillometry studies in the past have looked at the things like the peak amplitude from a very, very short stimulus, peak amplitude or the time to peak, these first two parameters. Connor, what you've done is look at the other side of this, which is the time to decay. So you peak up and then you decay over time, which is somewhat area under the curve, but also basically this time to decay, which is pretty unusual and pretty innovative in terms of pupillometry studies. What do you think that's indexing? And now this is hard because no one has an answer, so I'm not expecting an answer, but in your paper, you talk, you sometimes alternate between attention, arousal, people talk about cognitive load, people talk about surprise. All of those things could be happening. What do you think is happening?
It's a sustained version of all of those things, unfortunately. So it really doesn't have awesome specificity, which I guess is like the only downside of pupillometry is that, one of the downsides of pupillometry is that, it's always kind of context dependent. So, for example, in that paper that, was in the dissertation, I think it really is like, at least in the time window that it was significant for us, it's kind of correlating to like the second time that people have now heard the drum beat, and then, how quickly they get bored of it, and they're like, oh, I recognize this and I'm going to stop paying attention to it. So in that case, I think it's more of just like an attentional disengagement and like how quickly they get bored with it, because then after that they hit floor and the drift isn't so meaningful anymore. But in my EEG study, it was a lot more difficult to interpret because we also found drift rate results with that. But the thing is that like, it was essentially kind of a linear effect, but the drift rate was negative but approaching zero. So in that context, it was very difficult to interpret as like, well, is it getting to floor faster in the high condition, or is it already at floor? So I think, I like the drift rate. It works really well for certain things, but I think I have a better method for it now that I favor a little bit more. It's closer to the average.
Sorry. What individual differences do you think drift rate indexes? So one of the big things I was really excited about in your dissertation is this connection between attention and executive function, right? So you could imagine that someone with very good executive function peaks quick and falls to baseline very quick, right? And it's like a refractory effect. And the way you were just describing it is like, was more along an interest level, right? They just get bored over time and it drifts. So one could be executive and you do a quick return and you're ready for the next thing. The two is you just get disinterested and it comes down slowly. Now, is it the same answer on the last one, like maybe a little bit of both of those are happening, or do you think it's more executive?
Yeah, I mean, I'm going to go with the cop-out answer that it's, that I think there's two big schools of attention and like predictability. So like there is like the fluency kind of theory where yes, somebody who is like really good at allocating attention, they only pay attention when they need to, and then immediately they accelerate to the floor. So this would be a lot of the times like stuff like repetition suppression and repetition attenuation falls into this kind of camp. But then you also have the school who's, I think, gaining more popularity in certain flavors of predictive coding, whereas attention is kind of indexing precision weighting and that kind of thing. And so sometimes attention is turning up the gain. And unfortunately, in most of the studies that people do trying to test these things, they're confounded. The task kind of confounds whether or not, like, well, is it actually smarter to pay more attention, or is it more smart to like kind of like disengage and like save resources, So there's a lot more, people are testing this, but right now it's still kind of up in the air.
Do you think there are experimental manipulations that could get to that, whether it's whether it's interest or executive function, or would you have to layer in different measurement modalities. So for example, if you did combine pupillometry, fMRI, and had some specific areas of interest, would that tell you?
Yeah, I mean, all the repetition suppression stuff, or at least all the classic versions of these were like fMRI studies. So that would be one great way to test this kind of thing. But again, I think it's really, pupillometry as a measure of attention is as flexible as attention itself is, where it's going to depend on what the task is, what the motivation of the subjects is. Are you paying them to get right answers? Are you paying them to like kind of, do other things? Are you telling them don't pay attention to the stimuli, just read a book?
Yeah.
I mean, it's really, really context dependent. And I think maybe I should have been even more careful with like some of the interpretation of this stuff.
Yeah, I thought your interpretations are right and spot on, I think, in acknowledging the nuance and that there are certain parts that we don't know. Bruno and I were talking the other night at dinner, and Rolf, about limitations of fMRI and people sort of falling in love with this as the modality that can tell you everything. But when you have this temporal sampling that only happens, fast with a multiband every 1 second, you still have these beats that are happening multiple times in a second, and you're making a lot of guesses. Related to, so some of these questions I had in advance, but some just came up during your talk, so I hope, and some of them are weird, so you can say I don't want to answer that, or I want to move on. But I was curious about your brain, so some of your brain hypotheses, and really specifically about zeroing in the parietal lobe. And my question is, in this other world that I work on in language, people are really, really interested in speech motor timing, and they are very, very, and prediction, and they're very cued in on the basal ganglia, they're cued in on the cerebellum now. And I was curious, like when you, and again, this is very speculative, but when you want to go on and do intracranial work, where would you want to measure from, right? Where would you, in doing networks, getting to this, where would you really want to target?
I mean, I've been wanting to get into the amygdala and basal ganglia for years. But I will say that after meeting and working with people who work with intracranial data, it seems like way messier, and the signal to noise ratio is really great, but the problem is like you've got these significant channels that are responsive to everything all over the place. It's almost like the brain is way more connectionist than little parcels of like, oh, this does this does this. So I don't know. I mean, I would love to measure from basal ganglia because, again, for timing and for musical rhythm and especially like reward, utterly crucial. It's definitely involved. But I don't know, like the computational difficulties with intracranial recordings might be enough to deter me from wanting to do it myself.
Yeah.
But
and the idea that epilepsy, you're going to have these sources of epileptiform activity that are going to guide where these grids are, and so you might want the amygdala, but hey, we're not there, or hey, you might want the inferior parietal lobule, but hey, we don't have coverage there. Yeah.
So I mean, and again, this is really where open science comes in and like the collaboration. So the people here, they share a lot of data with Bob Knight's lab from Berkeley. And fMRI people are doing more data sharing with these big databases. And I think we're going to need stuff like that if we really want to tackle the nitty gritty of this.
Yeah, that's great. Okay, so one of my other questions, my next one, pupillometry, time to decay. Okay, my next one would be to walk us through, I wondered if you could walk us through kind of what's happening here. You have time here in milliseconds, right? And then you have the diameter in arbitrary units. And starting at 0, and just like what I was saying before, where you have this, basically this like very quick response that you're measuring from, which is like you have a baseline corrected in here. Walk us through what we're seeing, at least in terms of the peak and the decay and what it means. And also what it means in terms of you're falling below the baseline. What is that? How would you interpret that?
Yeah, I think I actually have...
let's trade.
Yeah, I have a plot here. It illustrates really nicely how I calculated the drift rate too, which I think is kind of important. But yeah, I mean, that first big bump you see is just the orienting response. So, something new is happening. Because before that, it was just a circle on the screen and it was silent. And so like, oh damn, like drum beats. Whoa, gotta pay attention. It's startling. Your pupil dilates, it goes crazy. Let's see. Can we see this? Oh, I'm gonna turn the lights off. I guess we can't see that. Beautiful. Now we can see that.
So maybe you could start with like, what's happening right before you start the measurement? So this is like the beats going.
Yeah. So it's in that experiment, it was 3 seconds of silence, which in hindsight, too long. Because you actually see kind of like a ramping up expectation, and then like also you see even a slight drift in the baseline period of 3 seconds. Granted, it's like we only took the median from the last 1 second, which is the standard, and then we just subtracted that from everything else. Let me see. I don't know where my mouse is actually. It's over here. Maybe I could just click.
Oh, yeah,
Yeah, so we got the graph up now. And so what you see is you see this big orienting response here, which, you know, this dip is actually just because like in the pre-baseline period there was kind of a drift already there. But then, you know, after like a very brief latency, you know, it shoots up around 1.2 seconds, 1.5 seconds or so, people peak. And then people get used to it. They're like, you know, it's just drum beats. This is the same thing I've been listening to for the last hour. These dashed lines correspond to when the drum beat is going to repeat, so when it loops. And so from here, we calculate the drift, you know, from the average of the first 3 time bins here and the average of the last 3 time bins here. And we do that for every one of these repetitions. And so actually, if I just hone in on the random just to illustrate this, you know, this would be a very, very, very slightly positive drift rate. This is pretty strongly negative, and then here it's like a little bit less negative, and you can see it's kind of bottoming out a little bit. Maybe less so in the random because, you know, it's everything is changing, so maybe not the best example for this one. But yeah, here I would say this is like the maintenance phase, where it's like, okay, how interested and how bored am I getting? And then around repetitions 3 or 4, people start to check out. And, you know, hilariously enough, like even when I did this with double the length of the trial, so like this is around 20 seconds long. In the EEG experiment, it was 40 seconds long. And it seems pretty universal. People seem to check out fully about halfway through. And it's at this point that, you know, you're maybe not, you're not so engaged. It's just kind of automatic kind of processing, I think.
Gotcha.
Does that answer the question?
Yeah, that's good.
Yeah.
And then you would baseline the next trial in this silence period after.
Oh, and so in this one we didn't have a silent period after. I mean, well, I guess nothing was playing, but like people were answering the questions. So they were saying, how much did I want to move? A lot or a little? How much did I like it? A lot or a little? And how energetic did that sound? Which again was our control question. And they would have as much time as they needed between that. So for that reason, we didn't really think there was going to be a whole lot of tainting from trial to trial. But we still did baseline correct at a trial level. So at the start of every trial, there was always 3 seconds of silence at the beginning, and then the drums started playing again.
Yeah, perfect. Okay. And then my next question is one that Elvira also had, and we talked a little bit about at lunch, would be this chicken and the egg question of when people enjoy beat and they love time and they enjoy timing, do you feel like they gravitate toward percussion or being a bassist, one of the instruments that really drives the meter, versus the other way around, right? And it's impossible to determine that. Do you go there because you like it, or do you like it because you're good at it?
Yeah.
But what are your thoughts? I mean, because you have all these people that you've sampled from for different instruments, and within that you have some percussionists and presumably some bassists.
A few of them, yeah.
Yeah, but I guess you didn't really look at the finer grain within those if they were.
Yeah, so we had a general class of instruments. So we had like percussion, strings, brass, piano, voice, and then other, which included like electronic production and stuff like that. And yeah, I mean, I would really love to dig deeper into that kind of stuff because, you know, there are qualitative differences about like, you know, as a bass player myself, it's like I feel like I might have a better sense of rhythm than, you know, certain kinds of guitarists, for example, especially like, you know, genre preferences I think play a big role. So like, you know, a jazz drummer versus just like, you know, a classical drummer who maybe only plays the bass drum or something like that versus somebody who plays a whole kit. So I think these things are really, really interesting to follow up on.
Yeah, I mean, and the other related question was this idea of just the nature-nurture question around are there people who exist who are just almost like the perfect pitch equivalent, but for beat? That they don't need any training, but they're right on, you know, milliseconds to milliseconds right on.
Yep.
And then the other side of that would be disorders, almost like a musia, or back to the brain, when we start talking about disorders of timing, like basal ganglia, when we talk about stuttering, or cerebellar ataxia, where people can't maintain a steady beat. So maybe can you talk a little bit about that spectrum of individual differences and being good at beat and being bad at beat, and how motor simulation plays into that?
Yeah, definitely. I mean, they were disappointing to me. But like this is the beat perception plot from the third paper, and so. Oh, sorry. Thanks. Get this a bit bigger. Yeah, I can take my glasses off too. Yeah, perfect. No, thanks. Thanks. Yeah. Yeah. So. This is all the subjects' beat alignment test scores across all 3 experiments that I ran for the PhD. Unfortunately, the EEG study didn't make it into the thesis in time. But I've scaled the size of these dots to reflect people's years of musical training. And so you can clearly see the confound here, where the active musicians are just the most highly trained musicians, and the inactive musicians had significantly less training, where the non-musicians by definition don't have any training. So, there is definitely like a nature-nurture question here, where it's like, well, maybe these active musicians, they were just good at it, and they kept up with it. But even still, it's like you see kind of a lot of variation here. So it's like, one person who has a lot of training, really, really high score, but then also you got people with like many years of musical training, and they're performing maybe not all that much better than some of the non-musicians, like this person here. And then even more curiously, getting to the deficit side of things, out of 110 participants, 2 people are like clinically beat deaf in the sample. So like this, and even more funny, this person here, the Combat scales from -4 to +4, and you can see that the majority of people are centered between -2 and +2. This person scored a -3 something, and they've got 5 years of musical training. So. It's clearly more complicated than just like, training will make you better. It didn't make this person better. But, they're an inactive musician, so, maybe the reason they stopped playing is because they got demotivated. They're like, I really just can't catch the beat. I'm done with this. I did my 5 years of piano training or whatever it was, and I'm done. So I don't know. It's really interesting, and I think we need to look into the genetic studies and these longitudinal and interventional studies. To really get at the real answer here.
Very cool. I guess related to that point would be I was wondering about my own experience with music that changes meters, and my inability to appreciate it. I can't listen. It just sounds very awful to me. This is very. It's almost blasphemy to say, like, when I listen to like late Miles Davis, super experimental, it just sounds all over the place, meters all over the place, and I can't listen to it. Now, I wondered with that is, what do you see as the relationship between changing meter and valence? Do people perceive it as unpleasant to do? And then with that, the other question I had would be, and would that be, since this is really an executive attention issue, like you can entrain to new meters if you have good attention or can upregulate attention. If you can't appreciate that, does it mean you're pretty low on executive function? I know that's kind of a leap to get to, or pretty speculative. Or if you have thoughts on that?
Well, I've got data
good.
on this kind of stuff, actually. Just an online study that I ran with some people here and in Canada. I'm not really familiar with this slideshow so much. But these are the responses to people's ratings of groove and pleasure in song clips that are either presented in 4/4 or half of them were in complex meters. So this included changing meters, included asymmetrical meters, all sorts of weird stuff. Basically just not 4/4. And what you see is the urge to move actually, doesn't follow an inverted U shape anymore in complex meters. They only understand and want to move to the simplest of the complex meter tracks. Whereas even mid levels of complexity and high levels of complexity, people don't want to move to it anymore. But curiously, that doesn't stop them from really liking a lot of the complex meter stuff. It turns out like a lot of these people, some of them are really, really low. But I think some people appreciate other aspects of the music that maybe aren't related to the meter or to the rhythm I think if you gave somebody a task like, okay, you have to tap along to this, I think you would see probably something that resembles more like this. But, if you're just telling them to sit there and listen to these tracks, rate how much you like them, people like to be challenged, I think.
Yeah.
But we don't like to get challenged too much.
Gotcha.
And so maybe that depends on executive functioning. I mean, it would make me feel better. I could go around telling everybody I'm smarter because I listen to goofy, bad music. But I don't know. I mean, we'd have to look into it for sure.
Yeah, I mean, I was curious, like if you spliced, sort of like the enculturation question around you being very used to a 3/4 or 4/4 beat, and then all of a sudden you switch to the West African, 3/3/2 or whatever. If people would feel that first of all, feel surprise, but some people would just they would so quickly acclimate to it or oscillate, basically entrain to that they they'd reach a steady state pretty quickly. But those people who don't have good attention that you could measure with a pupil response are going to be the ones that are like, I just can't hear that, I can't do that, I can't normalize that.
I mean, there's wild amount of individual differences present, I think. So expertise is part of it, executive functioning, I think, is part of it, and then I would say even probably personality differences. So things like openness to experience or maybe even agreeableness or something. Maybe these kinds of people would kind of, be more open, I guess, to being challenged, to having listening to weird things that they don't fully understand, but aren't necessarily frightened by.
Yeah.
And you can think of maybe the political lines that this kind of falls onto. But
I was curious too, if you're more likely to do this kind of stuff in the shower than you are in front of other people. You're willing to sort of dance and move around in the shower, but as soon as someone's looking at you, forget it, all bets are off. But you said most people in the lab didn't move a whole lot, right? Or do you sense that was out of shyness or just?
I think it's just the unnatural environment. It's like you're sitting in a little box, you've got speakers blasting at you, and then on top of that, you're being told, stare at the middle of the screen.
Oh yeah, it's a pupil.
So people did move, especially in the tapping experiment. So people's heads were moving and stuff, I guess, but when I looked at the number of frames dropped by the eye tracker and everything, it wasn't significantly different than when they were just sitting there. So I think the other thing is that when people are passively listening and stuff, they are still maybe moving or swaying, micro motion kind of stuff. Yeah. It's maybe not necessarily musical movement. Although I guess Alexander would know more about this.
One of the things they did, people in speech, there's this motor theory of speech perception that was big for a long time. This idea that as we're hearing words, we are simulating the articulatory movements that we need to produce the words. So about 30, 40 years ago, a big movement was to anesthetize people's larynx, right? And this idea is if you stop them from being able to simulate covertly, then they should be able to produce decrements in, they shouldn't be able to understand speech as well. So they did that a lot, and they found that it didn't matter that much. And so the speech perception world sort of went away from the motor theory. But it looks like the beat perception world is kind of going more toward it. I wondered, the TMS results, but if you were to paralyze someone temporarily, and look at their ability to either some outcome measure for beat perception, what do you think the sort of embodied component of this is? Do you need to move your body? Do you need motor system to do this, or is it sort of a ghost of stuff you don't need?
Yeah, I mean, this is the crux of the ASAP hypothesis. Are we just is this simulation or shadow? Is this necessary, or is this just a consequence of just beat perception? It's okay, there's some kind of simulation, but it's not really necessary. Where ASAP posits no, it is causally implicated. There's some kind of oscillatory coupling or some kind of top-down influence from the motor areas that literally shape the incoming sounds and stuff in the auditory stream. So I hope it's the latter, because I'm piloting this TMS experiment right now that kind of hinges on it. But check in next year. Maybe I'll have data to support it. But I hope it's the ASAP hypothesis.
I mean, it'll be really interesting from that standpoint of embodied cognition and the motor system, and how different people who are interested in tools, people interested in language, how they all sort of receive this in different ways. It'll be pretty fascinating.
And I mean, also if I'm gonna harken back to the trial lecture a little bit, like with some of those studies showing that, production abilities might come first. Like I think that kind of might speak to the primacy of being able to move our meat around over than just sitting there and contemplating and be like, yeah, that's where the beat's at.
Yeah.
Like maybe, I think it seems very plausible evolutionarily that, you need to like react, I think, faster than you need to like perceive.
Yeah.
So, from an evolutionary standpoint, I think there's also maybe an argument for this kind of thing.
Yeah, I think that's where language evolution is going, research was going too. That, really, yeah. And I think my last question,
We could switch back if you need.
I think if you want to bring the last slide up, it was just we can just hang here. I don't think that it's a data question. And you might have even answered it. Oh, executively expertise. I think yes. So, do people groove to what they perceive as? So, this was the valence question that I had about shifting meters and it being perceived as unpleasant. And then the first one was certain meters common in different music genres. You answered that. Oh, and then this idea of being able to switch between meters. How do you think that would relate to things like executive function tests, like the Wisconsin card sort, right? So if you're sorting cards that are all along one rule, like I'm color sorting and then I switch the task. Some people are good at that. Some people take a long time to learn the rule. Do you think it's the same process? And because in your first slide, in the neural part, you really, that top-down part, you link to dorsolateral prefrontal cortex, which is pretty heavy Wisconsin zone for executive function.
Yeah, I mean, so I think it really kind of comes down to how meter is being switched around. Because with the Wisconsin card sorting task, it's just kind of like random, right? The subjects don't know in advance when the rule is going to switch.
Right.
Whereas with music, the thing that makes music music and not just like, white noise out there is the fact that there is more order to it. And so people develop these expectations of like when the meter might shift or something like that. Or at the very least, they learn very, very quickly, just like I guess most people do with the Wisconsin card sorting task. So I think maybe it depends on like, is it free jazz where it's like totally improvised and everything? In that case, I think, it might be closer to the Wisconsin card sorting task, or at least the classical versions of it. But, the way that, metric shifts usually work in like Western music sometimes, I think, it's a little bit more predictable. And I think if people are encultured listeners and they know when it's coming, or maybe they just know the song and they know when to expect it, then I don't think it has like this jolting kind of valence effect, with the Wisconsin card sorting test. I mean, you definitely like, oh, no, what, I'm wrong? What?
Yeah.
Whereas like with meter, for stuff that people know and when they expect it, I think it's much more rewarding actually, rather than jolting.
Do you think the pupil response could index the surprise of a jolt too? When you suddenly change meters, like all of a sudden you think, well, something's really different. I don't know what it is.
Oh, absolutely. I'm sure somebody's shown this already.
Yeah.
And if they haven't, they should.
Yeah, I mean, that's one of those things you think someone must have shown it, but no one's ever did it. But it seems plausible given given what you're doing.
No, I mean, I see a big orienting response when the sound comes on, and then also in the EEG study, we had a silent window at the end for like neural resonance. So this is brain activity, oscillatory brain activity that's untainted by like the actual sounds that are coming in. So it's
just like a resting period, or
yeah. So it's just not entirely resting.
Or wash out.
We tell them imagine the beat continuing. Most people don't listen, and they just tell us, I forgot to do that like the whole time.
Yeah.
We still see interesting results regardless, but the thing is in the pupil data, we can't actually analyze that because you get a massive orienting response as soon as the drum beat goes off. So, I could imagine like a metric shift could be treated the same way where it's like, oh God, something new. Whoa, what's going on here?
Yeah.
And maybe it would be a sustained response until, you stay in that meter for long enough and you kind of get it, and then maybe you start to accelerate to the floor again.
Yeah, for sure. Yeah. I think those are all the questions I had. Thank you very much. Thanks.
Thank you.
I would like to thank the second opponent and the candidate for their efforts. No one has asked to speak as an ex auditorio opponent. If anyone wishes to do so, please speak up now. Would the candidate like to make any closing remarks?
Thank you for your time.
Thank you. The defense is hereby closed. The rector of the University of Oslo and the university board will be notified. I would also like to inform you that there will be a reception in the kitchen area of Fritmo downstairs at 3 o'clock, if anyone wishes to join. On behalf of the Faculty of Social Science, I would like to give you this gift over here.
Splendid. Do I open it here?
Please say the Congratulations. Fabula acta est.